Let's just jump right into it. Welcome to The Explainer. Today, we're taking a fascinating look deep underground, and honestly, we're diving into the harsh, undeniable physical realities of offshore engineering and reservoir management. You know, when a lot of people think of drilling for oil, they picture this massive geyser of black liquid just bursting to the surface, flowing endlessly on its own. But the reality of how a reservoir actually behaves is, well, it's a lot more stubborn than that. As any senior engineer will tell you, simply finding the oil is really only half the battle. Coaxing it out of the rock, that is where the real engineering against the limits actually begins.
And here's the harsh reality of reservoir engineering. Without human intervention, most reservoirs will only naturally produce maybe 10 to 30% of the oil they actually contain, meaning an astonishing 70 to 90% of the oil is just naturally left behind. Think about that for a second. Imagine building a multi-billion-dollar offshore platform, drilling miles beneath the ocean floor, and then leaving almost all of the product completely untouched. Obviously, that's not going to work. So that's the baseline we're working against.
So why does all that oil stay behind? Well, it doesn't just sit down there in some massive, hollow underground cavern. It actually exists within the tiny microscopic pores of solid rock, kind of like water trapped inside a dense, heavy sponge. It's physically held there by capillary forces, and as the reservoir pressure inevitably drops, that oil is increasingly replaced by water. In the very beginning, sure, the natural pressure of the earth is enough to squeeze some of it out, but almost as soon as production starts, that natural pressure begins to decline, and eventually, the reservoir simply runs out of the energy required to push that oil all the way to the surface.
So, to rescue these aging fields, engineers rely on a very specific toolkit. We're going to break down exactly how this is done. First, we'll look at the problem of pressure. Second, water injection and treatment. Third, gas injection and gas lift. And finally, deep well submersible pumps.
Okay, let's start with Section 1, the problem of pressure.
Deep underground, a reservoir is essentially driven by one of three natural mechanisms, and our primary physical obstacle out in the field is the loss of this natural motive force. First, there's solution gas drive, which is where gas dissolved right in the oil expands to push it out. Honestly, this is highly inefficient. Then there's gas cap drive, where a pocket of free gas sits entirely above the oil, acting kind of like a giant pneumatic accumulator just pushing downward. And finally, there's water drive, where a massive underlying aquifer expands and pushes the oil up from below. But here is the catch. Regardless of which natural drive you're lucky enough to have, over time, they all weaken.
It's pure physics. As oil is produced and removed from the rock, the pressure within that rock drops. It's exactly like how pressure drops in a tire as air escapes. It really is that simple. And eventually, the reservoir pressure drops below the flowing wellhead pressure, which is the force required to push that heavy fluid up miles and miles of vertical tubing. When that happens, the oil can no longer flow. The well just dies.
And this brings us to the definitive strategy engineers use to fight back. It's called Enhanced Oil Recovery, or EOR. EOR is essentially the catch-all term for everything we do to assist extraction, push way beyond that natural recovery limit, and artificially maintain reservoir pressure. Whether we're installing specialized mechanical equipment downhole or actively injecting water or gas back into the reservoir to replace the sheer volume of oil we've taken out, EOR is how we extend the life of a field and drastically improve the economics of the whole operation.
Moving on to Section 2, water injection and treatment. This is actually the most widely used EOR intervention in the world.
Because oil is mostly incompressible, taking a barrel out means you absolutely have to put a barrel of something else back in to keep the pressure up. And offshore, well, we happen to have an endless supply of seawater right there. We utilize what's called peripheral or flank water injection. Engineers drill dedicated injection wells right at the outer edges of the oil-bearing rock. Then, immensely powerful centrifugal pumps up on the platform push treated seawater down into these wells at massive pressures. We're talking up to 5,000 psi. That literal wall of injected water physically sweeps through the rock, forcing the trapped oil toward the production wells located in the center.
But here's the thing. You absolutely cannot just pump raw seawater into an oil reservoir. If you did, you would completely destroy a multi-billion-dollar asset in no time. Seawater requires a rigorous 4-stage treatment process first. Step 1 is coarse filtration, just getting rid of the marine organisms and large suspended particles. Step 2 is deoxygenation. Usually, we use a massive deaerator tower where the seawater contacts a countercurrent gas, like nitrogen or natural gas, which literally sweeps the oxygen out. We have to get dissolved oxygen below 20 parts per billion. Why? Because any oxygen would cause severe, rapid corrosion of the injection system and plug up the reservoir rock with iron oxide precipitates, basically rust. Step 3 is fine filtration, getting down to 1 to 5 microns so we don't clog the microscopic pores of the rock itself. And finally, step 4 is a heavy biocide treatment. We have to kill off sulfate-reducing bacteria, or SRBs. If they get down there, they sour the reservoir by producing hydrogen sulfide, a highly lethal and incredibly corrosive gas.
Now, stripping that oxygen out is usually done in those massive de-aeration towers I mentioned. But space on an offshore platform, especially on an FPSO vessel, is incredibly tight. Every square inch matters. So sometimes we rely on an absolutely ingenious alternative, the Minox Compact De-aeration System. Instead of a giant, heavy tower, this system uses gas-permeable membranes and a vacuum to just pull the oxygen right out of the seawater. It saves a ton of space, and amazingly, it strips that corrosive oxygen down to just 10 parts per billion. It's a perfect example of the hidden, intense complexity required just to make water safe to put into a reservoir.
Let's look at Section 3, gas injection and gas lift. Two totally different ways of manipulating pressure.
Gas injection actually works a lot like water injection. We take associated gas from production, or even purchased gas, compress it to an extreme degree, sometimes up to 12,000 psi, and force it back down into the reservoir rock. This replaces volume and maintains pressure, and it's especially effective for gas cap reservoirs. Plus, it brilliantly solves the logistical nightmare of what to do with produced gas when you don't have a pipeline to export it. But gas lift is an entirely different physical mechanism. Instead of pushing gas deep into the rock itself, we inject high-pressure gas into the annulus. That's the empty space between the production tubing and the casing. The gas is forced through special valves at various depths to bubble up inside the column of oil.
And the elegance of gas lift is truly something to appreciate. By aerating that column of oil with gas bubbles, we are drastically reducing its specific gravity. We're making the fluid physically lighter. And the lighter fluid column requires significantly less static head pressure at the bottom to lift it all the way to the surface. It is such a brilliant solution because it uses the platform's own natural gas to do the heavy lifting, all without requiring any complex, moving mechanical parts sitting thousands of meters downhole. But of course, there comes a time when the reservoir pressure is so completely depleted that even lightening the fluid with gas lift just isn't enough.
Which brings us to Section 4, Deep Well Submersible Pumps, our mechanical solutions of last resort.
When the rock simply cannot push anymore, we have to pull. We do this by installing an electrical submersible pump, or ESP, directly into the production tubing string, sometimes sitting up to 2,000 meters downhole. Let's break down the anatomy of this incredible piece of machinery. Right at the bottom, you have the motor. It's a long, slender AC induction motor. It has to be slim enough to fit inside the wellbore, but it is packing serious horsepower. Right above that is the seal section. This is absolutely critical, because it equalizes the pressure between the inside of the motor and the harsh wellbore, keeping well fluids from getting in and frying the electronics. Then comes the pump itself, which is made up of multiple centrifugal stages stacked on top of each other, continuously adding pressure to the fluid. And finally, running all the way back up to the surface, is the power cable, literally clamped to the outside of the tubing, delivering hundreds of kilowatts of power deep underground.
Now, ESPs are phenomenal, but they do have a major rival out there, the hydraulic submersible pump, or HSP. See, an ESP requires running a very vulnerable high-voltage electrical cable miles underground. An HSP avoids that completely. Instead of electricity, it uses surface pumps to drive highly pressurized hydraulic fluid, called power fluid, down the well to spin it downhole turbine pump. The huge advantage here is safety and durability. Zero high-voltage electronics downhole. But the trade-off, you have to constantly manage all that power fluid circulation. Because that hydraulic fluid mixes directly with the produced oil, your surface platform now has to do the extra work of separating all that additional fluid once it gets back to the top. Still, both ESPs and HSPs are unbelievable feats of engineering designed to conquer that loss of natural pressure.
So, why do we go through all this incredible effort, complexity, and expense? Because the stakes are absolutely massive. By utilizing water injection, gas lift, and submersible pumps, engineers aren't just scraping the barrel for a tiny bit more oil. These systems extend the productive life of a field significantly, very often by 5 to 15 extra years beyond what natural flow alone could ever achieve. They are a critical, indispensable tool in maximizing recovery from maturing offshore fields.
We are essentially transforming a dying asset into a highly productive one and bumping that total oil recovery up to 45%, instead of abandoning the well at just 20%.
Which leaves us with a really fascinating thought about the future of this industry. As these reservoirs mature, they naturally produce more and more water along with the oil, which severely chokes the surface facilities. The next major frontier we are looking at is moving these massive separation and pumping systems entirely down to the ocean floor. By separating the water right at the wellhead and injecting it straight back into the seabed, we completely eliminate the need to pump all that dead weight miles up to the surface. So, the big question is, how much further can these underwater processing factories push the limits of aging reservoirs well beyond the 15-year life extensions we are already achieving today? It is a genuinely thrilling frontier for engineering. Thanks so much for joining me on this explainer, and remember to always keep questioning the limits.